Thanks, Sujay. Thanks for inviting me. It's great to be here in Austin. So I work mostly on machine learning and been looking at privacy over the past couple of years. So this is about a problem in privacy that has, sort of contributes to and also draws from techniques from machine learning. So we'll see some interplay there. But there's a joint work with Kamalika Chaudhry and Shuang Zhang, both from UC San Diego. Okay, so I'm sure everyone knows by now that there's a lot of data that's sort of useful to for many different applications, and a lot of times this data is actually about individual people, and so you have data collected about people. For instance, maybe you collect their behavior on the internet, or you collect sort of information about their medical profiles or their genetics, and these can all be used for a lot of different applications. For instance, targeting content at the users based on their preferences. You can try to model things about diseases that people might suffer from. You can also try to learn about genetics itself, or genetic basis of diseases from individual people's genetics. So there's a lot of great applications. Well, maybe not. Some of them are not great from some people's perspective, but I say on a whole, a lot of interesting, useful application for society that we can derive by studying all of these data about individuals. So in the sort of later in the talk, I'll discuss two kinds of applications. One is just somewhat more practical application where you're looking at how people's purchasing histories on the internet or in any kind of transactions. And you see that people seem to buy certain kinds of items together, and you'd like to find out which are these kinds of pairs or groups of items that are most frequently bought together. So this is a well-studied problem in data mining called the frequent item set mining problem. But this is again based on individuals' purchasing histories, and you try to sort of look at all of this data to try to figure out what are interesting items that people buy together. Sort of more generically in machine learning, we look at the problem of supervised learning, where you're trying to find a classifier to classify instances by their labels. So think of X's as instances, feature vectors, descriptions of some objects. In this case, these objects are the individual people who are represented in a data set taken from some population. They can be classified, let's say, into just one or two different groups, 0 and 1. And the machine learning or supervised learning problem is to find a classifier that, as accurately as possible predicts the labels from just these instances, the feature vectors. And you would like it to be accurate on the population as a whole. Okay, but in a lot of these problems, the data that you get is actually a sample of the population, and you measure, their features and their classification for these particular individuals. So a lot of these problems, they can actually be cast in a very generic framework where you have data about individuals. Let's say you have a bunch of data points, one for every individual and different individuals, and you want to find some item, for instance, a classifier or an item set or some kind of object from some universe which has, potentially a very large cardinality. For now, we'll just think of it as a finite cardinality. And then there's some way to measure the quality of this item, the scoring function that takes an item and the data set and gives you a score. And you would like to find the item that maximizes this score. Okay, so the maximizes the classification accuracy that has the, the highest frequency in the data set or in the population. Some sense. So this is a very generic maximization problem that fits a lot of the problems that we study on based on these individuals' data. And this is sort of the subject of a lot of machine learning and data mining. Essentially, it boils down to some kind of optimization problem. Okay, so what's the privacy angle here? So the issue is that a lot of the data about individuals might actually be information that people are a little bit sensitive about, that they don't want to be unnecessarily revealed to the public if at all possible. So they maybe have contributed their data to this data set, to this organization, thinking that this is not going to be revealed to the public. But then, we would like to use this data to do some kind of statistical analysis to solve this this kind of generic maximization problem, because this is useful for many reasons. You can find classifiers that classify individuals based on these descriptors. But the output of this kind of analysis, may actually leak information about individuals represented in the data set. So in this kind of frequent item set problem, you might have the frequencies of how often people bought these different items. So it's a little bit too small to read here, but let's say in one data set, let's say in which person Alice is not represented in, you have these 4 different types of item sets. This one, let's say like wine and cheese, milk and eggs, fruits and veggies, soda and chips. And people in the data set bought these different item sets with these frequencies. So if this was the case without Alice's data, and if it turns out that if Alice was actually represented in the data set, that this is the profile of frequencies that you get when you include Alice in the data, then they can quite quickly change which item is the maximizer, right? So in this case, without Alice's data, it turned out that soda and chips was the most frequently bought item set, but with Alice's data, it's actually this other item. So there's in some sense a compromise of privacy here, because it could be that someone who's trying to snoop on Alice knows what the data would look like without her data, and then actually expects to see soda and chips, but then actually sees the output of the analysis on the data that contains Alice's data, and then sees that the most frequent item is now this other one, this wine and cheese. Then he has learned something about Alice, which may be something that Alice didn't want the public to know. So in this sense, this is kind of a problem where the adversary might have access to side information, in particular things about everyone else in the data set, in the database without Alice. But because of the output of the analysis, because of the solution to this maximization problem, has now learned something new that the adversary didn't know before. So this is the kind of a problem with doing analysis on this kind of sensitive data, and it seems to these kind of issues seem to come up in unexpected ways. So there's a big kind of ordeal with when Netflix ran their Netflix challenge and released the public data set. People were able to use side information, namely databases about other movie ratings, to infer things about what individuals represented in the Netflix data set. And so that's that was sort of an unexpected compromise of privacy just from this public release of, presumably they thought it was an anonymized data set. So it seems like maybe privacy is at odds with this kind of data analysis or machine learning in general, but I would argue that it's not actually, because the goal in machine learning or statistical learning is to somehow learn something about the entire population, but not necessarily about any individual. And in fact, the goal in machine learning, one problem that we actually specifically try to address is to avoid overfitting the training data. So you have some data set, you don't want to just have accurate classification on the data set that you have. You would like accurate classification on the entire population at large. And this is the problem that we have to deal with in machine learning all the time. So, we kind of expressly do not want to overfit the data set. We do not want to depend too much on any one individual's data. But nevertheless, the methods that we do have for machine learning, or at least many of the methods we have, do reveal information, do leak this kind of information about the training data. For instance, if you use the support vector machine method, then the individual data points might actually be part of the thing you release, part of the classifier that you end up releasing. So the support vectors in your classifier. So at least the goals are not, at odds with each other, but definitely some of the methods, are not privacy preserving in a sense. So there was, people realized this issue, and so in the theoretical computer science community and cryptography community, in this now famous article by Dwork, McSherry, Nassim, and Smith, they define a very nice privacy goal, which is that of differential privacy. And the goal here, sort of semantically, is that when you output something from your data analysis of this sensitive data, the information that anyone can learn about a person should not increase. And this is where the notion of differential comes in, is that you might have known something about these individuals before, but now that you've seen the output of this private data analysis, your information or what you know should not have increased by much. It should be limited in some sense. Okay, and so formalizing this goal is what they call differential privacy. But here's sort of a cartoon illustration of it. I'll give you the formal definition in a bit. But if you have some data set, and with a particular, and Alice, for instance, is represented in this data set, the analysis turns out has to be a randomized analysis, but the output of the analysis should be be drawn from some probability distribution. And the property of differential privacy, if this procedure is differentially private, then if you had replaced Alice's data with anyone else's data, for instance, Bob's data, the resulting distribution over which you draw your output should not be very different. It should be almost the same. So formally, what this looks, okay, so sort of from the perspective of Alice, basically if an attacker or if some adversary wanted to draw some conclusion about Alice after looking at the output drawn from this, then Alice really has some, can plausibly deny whatever inference this attack adversary is making, because you can say that, look, you would have seen basically the same thing if Bob was in the data instead.
Does this say anything about groups of individuals? So in particular, if the entire population is taken, of course you'll learn it. But what about pairs or triples? Does differential privacy say that I can't learn anything about small groups?
Yeah, so it composes in a bit, but basically what the adversary could know is, for instance, everyone's data except for Alice's data. And by looking at the output, you cannot learn too much even about Alice. So in fact, the adversary might have known everything except for one thing, which is actually quite strong. Sujay?
So is this really an issue when you only have very small populations? Because one would imagine that if you have very large populations, it's somehow naturally kind of private. Yeah,
you would think so. But I guess what you're kind of guard against is not an issue about the population, but the actual data set, for instance, first. But what we would like to be able to guard against is some kind of side information that tells the adversary everything about the data set, everyone in the data set, except for one person. So the size, in fact, doesn't come in there. But you'll see that the size of the data set does kind of come in other ways. We'll get to that in a bit.
I guess it's that they learn nothing more about Alice, because that could be a delta function. It could be that everybody buys wine and cheese.
Yeah, it could be that.
You do learn something about
Yeah, so it could have been that the adversary already knew everything there is to know about Alice anyway, but by looking at the output here, it doesn't learn anything new. So Alice could have been posting all of her information on Facebook, and everyone knows everything about Alice already. There's nothing you can do about that in this case. Okay, but here's the formal definition. So, a procedure that runs on some data set is epsilon differentially private if you look at any pair of data sets that differ in just one entry, one person's entry, D and D prime, then these procedures have to be randomized. That's the first thing. But the distribution over this procedure assigns to any set of outcomes when you have, let's say, the data set D prime, should sort of be the same up to a small multiplicative factor as what the distribution would have been when you had the original data set D. Okay, so think of this multiplicative factor, e to the epsilon, as like 1 plus epsilon. Okay, so if you think epsilon is small, then these two distributions do not differ much by except up to some small multiplicative factor. Okay, so of course smaller epsilon means some kind of stronger guarantee of privacy. Okay, so I won't really get into actual semantics of epsilon except beyond this point, because it's not, there are some semantics that you can derive from it, but just for the sake of this talk, just think of smaller epsilon being a good thing, meaning more privacy. Okay, and then there's sort of natural relaxations of this. So maybe you can't achieve this always, but maybe for, if you can achieve it up to some, up to events of some small probability delta. So you have a kind of a multiplicative plus additive closeness. Okay, so this is called epsilon delta differential privacy, or approximate privacy. Okay, so just to give you a warm-up, there's this problem of approximating the maximum of some function. So let's say you have some function g defined on your data set, and let's say it's smooth, or it's Lipschitz in this sense. So changing one entry in the data set isn't going to increase the function value by more than one. So sort of a simple fact, if let's say you have a collection of functions, f sub I, for all of a collection of functions indexed by I in this universe, and let's say these are all Lipschitz or smooth, then the max of these things is also going to be smooth. And then if this is the thing that you wanted to release, the sort of the value, the highest accuracy, or the value, the count of the maximum frequent, the most frequent item set, then a very simple procedure that you could do is to compute that max on the data set, and then add a little bit of noise. And the amount of noise you need is something that has standard deviation around 1 over epsilon. Okay, so the max, let's say this is a Lipschitz function, so it's anywhere between, let's say, like 0 and n. If epsilon is not, this thing is, can be rather small. This is just a constant with respect to n. So if you draw this amount of noise with respect to this distribution called the Laplace distribution, which sort of perfectly has this nice exponential form, then it turns out this procedure will be epsilon differentially private. Okay, and the whole reason is just because that this function is smooth, and so you're not shifting the distribution by much. Okay, so this is one of the simplest examples of a differentially private procedure. Note this is very different from what we're trying to do. This is just releasing the max rather than the argmax. You would like to release some actual item that is close to the maximizer. Okay, but here's the actual problem that we care about. So again, you have some data set of individual data points, and there's some item of some universe of items, u, and a score function that we'll assume is Lipschitz. And the goal is to find the item such that the score is as high as possible while satisfying differential privacy. Okay, so just to formalize it again, so for every item, this function value is going to be Lipschitz. It doesn't change by more than 1 when you change one person's entry. Okay, so the classical solution to this is actually something that looks a lot like the procedure I just described in the previous slide. This is due to McSherry and Talwar. What you can do is to sort of define some kind of discrete version of this exponential, of this Laplace distribution. The Laplace distribution is sometimes called a double exponential distribution because the tails are just both exponential tails on the left and right. So you can define something quite similar to this, where you're going to release one of the k different items. You define a probability distribution over these different items, and you choose item I with probability proportional to some exponential function of its score. Okay, so it turns out just use e to the epsilon over 2 times the score. And this is differentially private, simply because of the fact that these function values are smooth. They don't change by more than 1, and therefore the distribution cannot change by more than a multiplicative factor of e to the epsilon. So that seems like this is sort of the first method that you would try to solve this differentially private maximization problem. but it has some drawbacks. Okay, so the main drawback is that it's somehow inherently dependent on the number of items in your universe. Okay. Right, so the best kind of bound you can actually get, there's a lower bound on the value of the item that that this exponential mechanism returns, which that it's always going to be off from the maximum value by at least this additive amount, something log k over epsilon. Okay. With some constant probability, because these are all randomized procedure. But with some constant probability, you're at least this far away from the maximum value that you could have achieved. Okay, and this is even when there's sort of one obvious maximizer. Okay, so in this case, with one really obvious maximizer, the exponential mechanism puts this kind of distribution on it, which seems like it might be quite good, but in fact, unless you're still assigning quite a lot of probability mass to all these other items. In particular, if there are many, many items, then you can be at least this far away from the maximum value. So it turns out this is not just something specialized to the exponential mechanism, but in fact for any epsilon differentially private procedure for this problem, that's sort of inevitable. So for any algorithm that's differentially private, just by this constraint of having the output distribution sort of being smooth with respect to changes in the data set, that already forces you to have some dependence on the number of items in the universe. And so with at least probability half, you will inevitably be at least log k over epsilon away from the max. But again, this is actually for problems where there's only one item that's sort of the construction for this lower bound, which is sort of a classical lower bound for differential privacy. This is the construction sort of has one item that's just exactly this amount away from much larger than the rest, and it seems like maybe so in this case maybe it really is difficult. So, almost all the items are pretty close to the best one. But you might be able to hope that you could do much better in favorable cases. Okay, so what if there's only one item that's, or maybe a small number of items that are near maximizers, and everyone else have very low scores. Okay, so in these more favorable cases, you might hope that there's a procedure that does better. Unfortunately, the exponential mechanism is not that procedure, and that's because sort of the exponential mechanism is designed for this worst case scenario. That's actually kind of the case for a lot of procedures that satisfy differential privacy. They're all sort of geared towards the worst case. And this is kind of problematic for applications in machine learning and data mining, where you might think that the reason machine learning and data mining works well in practice is not because it seems to one conjecture for why these methods work so well is because somehow the world is not inherently adversarial. It's not constructing instances where there's only it's really hard to pick out the best item. There's more the world is more friendly to you, and there's really there's almost clearly only just one good item that you should choose from. So a basic question is whether we can design differentially private algorithms or approximately differentially private algorithms that avoid this kind of explicit dependence on the worst case, on the number of items or the size of the range. And so people have tried to address this in the literature. There's been a couple of papers in the past couple of years that look at specific problems and can actually avoid explicit dependence when they make certain assumptions about the data that you receive, or if they're only applying to very specific kinds of learning problems. So we're trying to look at now, so what we would like to do is try to generalize this, to look at a very general kind of private maximization problem and see what is the best thing that we can do. And there's sort of, as an aside, there's a related issue in statistical estimation. So if you're trying to estimate some functional of a distribution, And let's say this functional can take values in some range, between tau 0 and tau 1, over some family of distributions. Some previous work that I did with Kamalika, we showed that somehow even this estimation problem, things are inherently range dependent, at least in the worst case. So there are some worst case distributions for which the accuracy of your estimator, any differentially private estimator, has to inevitably depend at least somewhat on the range of the values that it can take. So somehow the log of the range is inevitable in the accuracy. So that's sort of seems like a related issue that comes up in estimation, not just maximization. Okay, so what do we do yeah?
This last result is also a worst case result. This last result is also a worst case kind of result.
Yeah, saying there's some worst distribution in this family of distribution that forces any algorithm. Okay, I mean, for any algorithm, there is some worst distribution. Yeah, so it's also a worst case thing. So we might hope, again, that there's something better you can do. It just sees the output once. Yeah, but what we're trying to guard against is that the adversary has all this side information about everyone else but one person, for instance.
So you don't generate a new random.
Yeah, no, so you can just see the one draw from this case. Okay, so what do we do about this private maximization problem? So what we define is some kind of parameterization of how easy the problem instance is. We call this a large margin concept, although it's kind of different from large margins and other machine learning problems. But it's some way to parameterize how easy the problem instance is. So that's the first contribution. The second contribution is a lower bound in terms of this parameter, the large margin parameters, that for any approximate differentially private algorithm has to somehow depend on this parameter. So it seems to be sort of the right parameter, and that's because we actually have an algorithm that achieves the upper bound, or something very close to the upper bound. Okay, that somehow automatically adapts to the easiness of the problem. So, maybe the problem is not that easy, in which case we sort of fall back to the worst case guarantee of log k over epsilon. But somehow the problem is actually a little bit easier or a lot easier, we kind of adapt to that and do much better in these cases. And this is sort of more in line with what we expect machine learning to be able to do. Okay, so for the rest of the talk, I'll kind of describe this large margin property, and then kind of sketch for you the algorithm and the analysis a bit, and kind of go to these applications in data mining and machine learning. Any questions at this point? Okay. All right, so let's kind of consider a very simple motivating case where what we're going to assume is that there's one best item for the data set, and then the second best is actually much worse. Okay, so for instance, these are the 7 different items that you might be able to output. The yellow one is clearly the best in terms of its score, and then the second best is much worse. There's some gap between the best and the second best. Okay, let's say the gap is about this much. For some value of delta, but let's think of it as constant, just like 1 over epsilon better. So you might hope to be able to take advantage of this. Okay, so what doesn't work? Okay, you can't just always return the best item. Okay, this turned out not to be private. First of all, this is deterministic, so it clearly does not work. But here's a clever idea from Smith and Takura. So what we're going to do is to look at whether there's a gap between the best and the second best, but then perturb that gap. So you look at the values of the best and the second best, and then you somehow perturb it, again using this Laplace distribution. And you check if it's big enough. Theta here will be log 1 over delta over epsilon. If indeed there seems to be the gap, then you return the best item. If not, you fail. You return some failure signal. Okay, so why does this work? So again, you use theta as log 1 over epsilon. Well, since this function, these are order statistics of And so these functions, sort of the best, the maximum, and the second maximum, these are both also Lipschitz functions, because we're assuming that f for any item is a Lipschitz function. So the chance that you fail is actually quite similar for both. In it cannot change too much. And it's because you fail exactly when sort of the actual gap is sort of bigger than some threshold value, and that won't change too much based when you change one item in a data set. Okay, that just follows from the property of this Laplace distribution, the fact that it exactly has this double exponential tail. And therefore, if they're really somehow the gap is sorry, it should be yeah. So you sort of overestimate the gap. So let's say the gap was less than theta over 2. You're only going to overestimate it and say that it's bigger than theta over 2 with some small probability delta in that case.
So why Laplace? If you have taken a Gaussian distribution, what would have gone wrong?
Gaussian would also work. Yeah, so it sort of looks a lot like the Laplace in some small narrow region. Sort of in the extreme tails, that's when it starts to be much different.
Distribution for that exponential of epsilon to come.
Yeah. So somehow it's like it would be sort of almost the same. Sort of when you get to the tails, then it gets to be a bit different, but that's sort of maybe contained in this delta probability mass anyway. It's just that we use this Laplace distribution because it exactly has this exponential form, and the definition is in some sense designed around that. Okay, so something like this where you test for the gap, but you do so in some kind of smooth way, some differentially private way. You test whether you're in this favorable situation, and then you exploit it if you can. So that's great for this one case where there's one obvious maximizer and all the other items have low scores. But this procedure will fail. Clearly it fails if there are just 2 items that have a very large score and everyone else is small. Okay, so so sort of the obvious way, natural way that people have thought to generalize this was to check for a gap, let's say between the rth best and the r+1th best. But this kind of gives you a suboptimal generalization. So you could do something like this, but it's it doesn't adapt to something very natural. Okay, so what is sort of our generalization of this? It's actually quite simple. First set up some definitions. So let's say f super r is sort of the rth highest value. Again, these are just the order statistics. And we can break ties however you like. So we'll define this concept, which we call an L gamma margin. We'll say that the score function in the data set has this margin of L gamma if the best item is bigger than the L plus first item, best item by at least gamma. So what this means is really that there are only L items within gamma of the best item. Okay, so this is a parameterized notion, a parameterized concept. So for instance, let's say this is gamma 1, then this particular data set and score pair has a 3 gamma 1 margin because there are only 3 items within gamma 1 of the best. But it also has a much bigger gamma 2 margin with 4 items. So now there are only 4 items. This is also the case that there are only 4 items within this gamma 2 value of the best. Okay, so that's our this concept of what we call the L gamma margin. So this is a bit different from this previous concept that people had been considering of looking at a gap between the rth best and r plus first best. This we're looking at a gap between the best and the L plus first best. Okay, so where does this come from? It actually comes from, we kind of took motivation from statistical learning. So this is, when you look at statistical learning problems, you're trying to learn classifiers that have low error or that have high accuracy. And what's sort of been now sort of well understood in statistical learning is that really the difficulty of the problems there doesn't depend on somehow the global structure of the problem about all the possible classifiers that you might consider, but it really only depends on some kind of notion of local complexity, sort of the complexity of classifiers or the space of things that you might want to consider just around the best classifier or the true classifier, if there's a true classifier. Okay, and this has sort of appeared in the forms of things called local Rademacher complexities or shell decomposition bounds. And so sort of in general for this kind of general maximization problem, it seems like the real complexity of the problem is how many near maximizers there are for a particular problem instance. Okay, so what we're able to do, we can actually show a lower bound in terms of this property. Okay, so you might ask for any given value of L, what should be the right value of gamma, and this is what a lower bound can shed light on. So what we're able to show is that if you have any differentially private algorithm with parameters epsilon and delta for sort of a small enough delta, delta should be less than epsilon over L. There's going to be some problem, some kind of private maximization problem that satisfies this large margin property with the margin of log L over epsilon, for which any such differentially private algorithm this differentially private algorithm will not be much more closer to the max than this amount of log L over epsilon. So you at least have to be at least this far away from the max. But this can be much better than for any given problem instance. If the problem instance really does have this amount of margin, then this can be much better than a log k over epsilon for very large values of k. So in statistical learning, log k is essentially some kind of worst case complexity of the problem, and you can think of log L as more of the local complexity of the problem. Okay, so this is a lower bound for any differentially private algorithm. And one thing to note is that it in particular rules out delta being 0, which was this kind of pure privacy case, because if delta is 0, then there's no way for you to even have avoid the log k. But we can hope to at least match this with sort of epsilon delta private algorithms. Okay, so here's our hope is that we can achieve some, if indeed the instance does have this kind of margin of L and maybe log L over epsilon margin, then we would like, with high probability to be able to return an item that is at least log L over epsilon close to the maximizer. Okay. And so we almost do this. We indeed do need to pay an extra log 1 over delta. Okay. But that's what we can achieve with our mechanism. So let me kind of quickly sketch this thing for you. So it's sort of broken up into 2 steps. What we do is we first try to test for whether the problem instance does indeed satisfy this property, that there really are only L items within gamma of the best, and gamma will be this log L over epsilon. So we want to find the value of L for which this is true. So indeed, L can be, in the worst case, equal to K, in which case it will always satisfy, but we might hope to find that it satisfies it for a much smaller value of L. So we do this test, and if indeed we find that it satisfies this for some small value of L, then how can we exploit it? So that's exactly our procedure. It's in 2 steps. We find the value of L such that the problem instance has this margin. And then what we do is something that's actually quite simple. We just run that previous kind of worst case algorithm, but restricted just to the top L items.
So I have a question.
Yep.
Why does the finding of L have to be differentially private? Because if I'm somebody who holds the data set, I know everything anyway, and I'm the one picking L. Right? So it's just a question of what I release should be differentially private. But L is like a parameter in my algorithm.
Yeah, well, it could sort of it could influence what you end up releasing, right? Right. So, for instance, let's say you just check for whether there's a gap between the first and second best, and then if there's a large gap, then you always release the first one. Well, then that means there's no chance that you ever release the second one, in which case that's not differentially private.
Well, not necessarily, because you don't need to do that. You check, but then you probably randomize in the second step.
Yeah, so if you did randomize in the second step, you could do that, yeah. Yeah, so yeah, it's true that in this step, it's not clear that because you don't actually output something here, that this part had to be differentially private. But if you sort of took care of that altogether here, you're right. It turns out the way that we do the analysis, it's sort of easy to just make sure this part is differentially private, and then even the value of L is differentially private, in which case even that could be public information. So it just makes for easier analysis because of some of these composition properties. But anyway, that's exactly what we do. I'm sorry, go ahead.
Would that mean that if L is not differentially private, and if you just run
The exponential mechanism?
I mean, okay, I guess what I mean is, could you somehow overestimate L?
Yeah, that might.
Exponential mechanism.
Yeah, that might work.
The thing is that for a fixed L, finding it is almost trivial.
Yeah.
But finding a differentially private L may be much less trivial.
Yeah, so it could be that you find some over approximation that sort of guarantees that the second step is always differentially private. That might be okay. But, right. So what do we do? So we do end up, just for the sake of making this easier to analyze, we make sure that the first step is also differentially private. And we essentially just use this randomized test of Smith and Sakura sort of for every possible value of L. We check if there's a large gap between the best and the Lth, L plus first best. And we try to do this in a way of increasing L's so that we will definitely stop after the smallest or a small enough L. And this overall procedure will be differentially private. And then in the second step, well, this turned out to be also an instantiation of this other technique due to Hart and Rothblum called the sparse vector technique. But then the second step is exactly just running the standard worst case procedure, but restricted to a smaller subset. Okay, we just pick the rth best item with probability proportional to e to the epsilon over 2 times the rth's largest score. And if indeed the data set did have this margin, then the algorithm overall will be epsilon delta differentially private. Okay. So the kinds of guarantees that we have are sort of the standard ones. This is like the safety guarantee that this procedure is definitely differentially private with parameters 2 epsilon, 2 delta. But for the more useful guarantees, the utility guarantee, which says that if indeed the data set did satisfy this large margin condition, did have this large margin, L and log L over delta over epsilon margin, then we definitely release an item that's close to the best by this amount, log L over epsilon, with high probability. And just for comparison, the lower bound, just essentially removed didn't have the delta in there. We think that maybe you could put the delta back. But that's the lower bound, and the exponential mechanism, even in cases like this, definitely had the log k, the worst case complexity there. Okay, so I'll just kind of sketch the analysis very briefly. There's this first phase that is essentially just an application of this previous work by Hart and Rothblum on the sparse vector technique. What you're trying to do is answer a bunch of queries, but you hope that there's only one query that you really have to answer. And that's, you can kind of view what we're doing in that way, in some sense. We just have different kinds of queries that we're trying to ask about the data set. Anyway, I won't get into details of this one, but the upshot is that it's differentially private, and also we only overestimate the margin with small probability. So if you really didn't have this margin with L and gamma over gamma, this thing with the log L over epsilon, If it didn't have this margin, then we say it does only with small probability. But given this, the rest of it is actually rather simple. We're just going to run the exponential mechanism on the top L items. Let's call this procedure EM sub L. And the reason this is differentially private, well, you just look at any neighboring data set. This can't change these score functions by too much. In particular, if there's some item that's sort of in the top L for both data sets, both the data set, your original one and the neighboring one, that changes one person's entry, if the item is in the both, it's in the top L of both, then we're exactly doing the exponential mechanism, and we knew that that was differentially private. If it was only in the top L for one of the data sets, but not the other one, not the neighboring one, then it means that you couldn't have, that item has to be has to be far from the best one in some sense. So the chance that you would have outputted that under one of the data sets is going to be small, something like delta over L. And this is just because of the large margin that exists in the data set. And so the upshot is that for any event, the two different distributions under neighboring data sets exactly satisfy the condition you need for epsilon delta privacy. And then just sort of putting everything together, since the first step is private, the second step is also private, together they're also differentially private, just by composition rules. Okay, right. Okay, so a recap of the main theoretical results. Let me kind of just quickly wrap up with some of the description of applications. So when do we kind of expect large margins to exist? You can kind of draw these nice histograms, and you can kind of pictorially see what it means to have a large margin, but in what kind of applications might you actually expect for these things to exist? One is that maybe the number of near maximizers is just limited by the fact that you have a finite data set to begin with. That will be the reason in the first application, this frequent item set mining. And then the second is sort of this statistical learning reason, because somehow the true complexity is really only determined by the number of near maximizers. Okay, so remember this frequent item set mining problem. Let's say you're a grocery store and you track what items people tend to buy together, and you want to try to find the item set that people seem to buy together the most often. So there's a lot of work on this problem, especially from a privacy perspective, because naturally this is a question that comes up a lot when you analyze people's data. So people have proposed using, for instance, the exponential mechanism for solving this problem, and then just more generally, they saw that this was a problem of dependence on log k, even in these favorable situations. A lot of works have tried to get around that by sort of relaxing the goal in some sense. So we can try to directly attack the original goal, find an item set that has as high frequency as possible. So this naturally fits in our problem where sort of the data are different sets that people could have, different sets of items that people could have bought together. And again, the items, the universe of items is again different subsets of grocery items that you might care about, like wine and cheese, milk and eggs, and so on. And so just because you have a finite amount of data, you're already limited in terms of the number of item sets that actually might occur in your data. And that already bounds the number of, you never have to explicitly depend on the cardinality of U just because you have a finite data set. So if the most frequent item occurs at least log L times in your data set, log L over epsilon log L over epsilon, essentially, then using this large margin mechanism will return an item set that's, roughly, let's say, within a constant factor with a constant fraction of that frequency. Okay, so that's sort of one really simple application where, the inherent complexity is limited just because of the finite training set, and this algorithm is able to exploit that. sort of from a more theoretical perspective, we can look at this general pack learning problem in supervised learning. So in pack learning, what you would do is you assume that your data set, which is pairs of features and labels, this data set is an IID sample from some distribution, and your goal is to find some classifier or hypothesis that has small prediction error. Okay. And we would like to do this in a way that preserves differential privacy. So one of the earliest papers that addressed this problem sort of proposed using the exponential mechanism, as you might expect. So first of all, this only works when you have finite hypothesis classes, and you get kind of the thing that you might expect. The error of the hypothesis you return is almost as good, sort of this far from the optimal that you could get. So you have some part that that's sort of inherent to the problem itself, and then another term that's based on due to privacy constraints. And actually generalizing this beyond finite classes is actually rather difficult, especially, at least if you care about continuous domains. For instance, if you have real value feature vectors. But even with finite hypothesis classes, you might hope to get some kind of local complexity bound. And so some work, you could look at local Rademacher complexity, but there's actually a really simple notion due to Langford and McAllister. We call it shell decompositions bounds, where you sort of just kind of split up the hypothesis class into these different shells based on how accurate each classifier is. Okay, so you consider the teeth shell being all hypotheses that are within this t times this factor away from the optimum error. So here D is the VC dimension of your class. Let's think of it as some worst case, some natural complexity of your class. And this actually, even for infinite classes, these shells could possibly be finite and small for at least small values of t, even when the total cardinality is infinite, or potentially very large. Okay, so what do you get when you use the large margin mechanism? You essentially get to replace the log cardinality with the cardinality of sort of some shell of the hypothesis class. So you just pick the largest t star, or the smallest t, such that this inequality is true. Okay, so eventually, if you set t large enough, this should be true. And then sort of that shell is the one that really determines the complexity of learning or private pack learning. So the error bound we get with the large margin mechanism is one that is at most this much away from the optimal, where now we replace log cardinality of h with this size of the t star shell. Okay, so really just the privacy penalty you pay really only depends on the number of hypotheses that have near optimal error. Okay. So there's actually a lot of improvements. We could hope to sort of improve get bounds that also, in this part, the non-privacy part, also depend on some local complexity measure, but at this point we don't quite know how yet. Okay, but that's, let me just wrap up. So I think this kind of problem of sort of looking at how easy, parameterizing some kind of easiness of the problem instances is sort of essential to really make differential privacy more practical, especially in machine learning problems. So what we proposed here was some new concept called what we call the large margin concept that provides you some way to smoothly parameterize how easy the particular maximization problem is. And the algorithm we propose is sort of nearly optimal, at least for under this parameter, because this pretty much closely matches the lower bound. And you can see that this kind of concept does apply in some sort of data mining and machine learning applications. So clearly we would like to definitely see where other problems where this kind of concept can give you improvements. And what we really need is an empirical evaluation of these kinds of procedures. Right now there's some constants involved in the bounds that we get that make it not so practical yet. And then just more generally, how do we sort of exploit non-worst case instances, the easiness of problem instances while guaranteeing differential privacy. Okay, that's it. Thanks.
So suppose, right, so what happens when all of your L gap is like log L over epsilon? So it seems like every single one of your shells doesn't quite hold, so you don't get a theorem, but it still has some amount of way in which the first one is easier.
Yeah, so you're sort of saying at every L.
It's because it barely doesn't hold.
Yeah, that's one kind of problem with at least the procedure that we have right now. There seems to be, like, if you're off by some constant factor, that you might not declare that, yes, there was a L gamma margin there. It seems like what we might be able to do is to sort of shift the gap by some amount and then test for sort of do the test, but then sort of say that, okay, it might not have an L gamma margin, but maybe has like 2L gamma margin, and just run it with the exponential mechanism with 2L instead.
And so I guess your lower bound for this is probably similar to the lower bound for just the K, where it's like L minus 1 guys are just barely, are all the same.
Yeah, but you could just say, run the now just, if it doesn't hold for L, it should hold when L is doubled, for instance.
But it seems like if you have conditions like that, then whatever your condition is, if it's just barely not in that condition, it might still be an easier problem.
So it definitely is still, I'm saying that sort of we can, if it just barely failed for this value of gamma at L, then, but it should hold, let's say, with 2L. And then we can just modify the procedure to run the exponential mechanism on 2L.